First of all, I want to introduce myself. My name is Donal Skelly, and I am a product manager at Serveron, which is a Qualitrol company. The presentation we have today will take a short look at some mechanisms by which it is possible to calculate the cost benefit of online transformer monitoring, or put another way, the return on investment that could be expected from deploying online monitoring. While we will show some examples to the actual process to calculate the cost benefit for an individual utility or company would need to be done on an individual basis. That is, there is no catch-all calculation. There will always be situation specific. So what we are doing here is looking at the basic background to cost-benefit calculation and showing some examples to illustrate that a dollar value can in fact be calculated. So first of all, what is covered by the term monitoring? This can be divided into two broad groups. So there is traditional monitoring and advanced monitoring, and generally we would consider traditional monitoring perhaps to be something that would be already in place on your transformer, or would be a relatively low-tech type of monitoring. So offline annual dissolved gas analysis is practiced by almost everybody. Temperature monitoring of the transformer, transformers in almost all cases will have temperature gauges. Load current and voltage monitoring, pump and fan operations, all the type of data that you might already be getting from your transformer. Advanced monitoring then would cover such things as online DGA, dissolved gas analysis, online moisture in oil, partial discharge either offline or online, bushing, power factor and capacitance. So more sophisticated monitoring systems. DGA is generally considered the cornerstone of any online monitoring system and is the general basis of this discussion. However, this should be considered in the context that Serveron specialize in DGA monitoring solutions. Generally, DGA systems, including those manufactured by Serveron, will provide some or all diagnostic gases, plus moisture in oil, plus transformer load, perhaps, plus temperature, perhaps. And a combination of these can be employed to detect actually the majority of main tank faults. However, in the wider context of overall transformer monitoring, you can consider that it might include partial discharge, bushing monitoring, advanced temperature monitoring, for example, with fiber optics, etc. And in that context, and including the Serveron DGA equipment, Qualitrol do provide a full range of technologies needed to achieve this comprehensive monitoring. So while DGA covers a majority of detectable faults, the actual calculated values that we will look at are not specific to DGA. The benefits from online monitoring are proportional in many regards to the quantity of monitoring that is deployed, and of course the cost is in some way proportional to that too. So essentially, the more one spends on monitoring system, the more potential savings associated with the various mechanisms of savings that we will discuss can be realized. The standards, so these standards are the primary source of information that I have used to construct the presentation. And in particular, I guess it's worth saying that IEEE C57143 2012 is a comprehensive guide that could be used to construct your own financial analysis and is the major source of reference in this presentation. So how do we calculate the cost of monitoring? This is actually a pretty straightforward calculation. If you know, for example, the costs from the manufacturer, It's illustrated here in general terms, but there may be additional costs that might apply. For example, a company might consider the cost of a truck roll when annual servicing was taking place, for example. So we're looking at the cost of purchasing the equipment initially, the cost of installation, whether it be done by the utility itself or by an external contractor, the cost of training, if any is required, or if there's any associated cost, the cost of maintenance, and then the operating cost of the equipment itself. And this is the basic equation, and the answer, of course, to that equation is the dollar cost of the monitoring. So it's not a particularly difficult calculation once you have an idea of the cost from any particular manufacturer. So now that we have a basic equation for the cost of monitoring, we should look at the benefits of monitoring. So there are two types of benefits: measurable benefits and tangible benefits. So those are perhaps benefits that you definitely know are there, but are a little bit more difficult to quantify. So to start with measurable benefits, the reduced inspection and maintenance costs associated with having monitoring in place. There will be, it would be envisaged reduced inspection required and associated reduced maintenance. Reduced failure-related repair or replacement costs. So the premise would be that by monitoring, you could cut down the costs associated with repair or replacement by having advance notice. Improved real-time transformer loading capability, whereby if you have an insight into your transformer's condition, you can be more proactive in dynamic loading of the transformer. Deferred upgrade capital costs due to load growth. So where transformers are starting to be overloaded, perhaps as load growth occurs, if you have monitoring, you can potentially defer upgrading that equipment by carefully monitoring as you increase the load. And then one that we will look at in a little more detail later on, deferred replacement capital costs due to equipment age or conditions. So all transformers will fail. Monitoring them will not prevent that failure, but it can potentially defer the failure by giving you better insight and therefore better capability to maintain the equipment in working order. And then the tangible benefits, benefits that you know exist but are hard to quantify. So enhanced system reliability and availability with fewer unplanned outages, improved planning for scheduled outages by using remote equipment condition assessments to avoid additional outages, enhanced financial results with performance-based regulation, where performance-based regulation exists and it doesn't exist in all states or all countries. Optimized design and operating practices, increased equipment life, enhanced personnel safety, and the potential for improved environmental safety. Again, tangible benefits, they are real, but they're hard to measure. Okay, so there are many benefits. How do we go about quantifying them and eventually put a dollar figure on that? So it is challenging to assess the benefits in a purely financial term, but there is essentially a fundamental equation. And this would look at the probability of a failure event occurring times the financial impact of that event on the asset owner, and that can be used to calculate the financial benefit of monitoring. So first, we need to calculate the probability of a transformer failing, and this can be a complex proposition if you're trying to calculate it for a specific population or even for a specific transformer. So in that case, you would need to consider three things. The first would be the number and age of transformers in the population, if you're looking at a population level. the health of each of those transformers based on your knowledge of your assets. And then perhaps the prevalence of known design issues. So we do know that some transformers, due to design issues or due to the fact that they were designed many decades ago when knowledge was not as good, that may need to be taken into consideration. In a case where that is difficult, or perhaps because of loss of knowledge within the utility impossible, then a simpler approach, and one which is recommended by IEEE, is that you would simply look at the historic failure rate and use that as a baseline. So IEEE suggests a 1.5% annual failure rate is reasonable as part of a general calculation, and this is in the context that for a highly reliable grid, 0.5% would be typical, and for infrastructure where there is unreliable equipment, maybe up to 3% would be a reasonable failure rate that you would see. So 1.5% could be used for these sorts of generic calculations. So as mentioned before, IEEE C57143 is the basis of this analysis. And this is how they have approached calculating the probability of a failure occurring with and without monitoring. So first of all, you need to consider the probability of a failure occurring at all. And then in that context, you need to work out the probability that a failure will be detected, either with online monitoring or with traditional monitoring. And not all failures will be detectable. And then you should calculate the probability that those failures will be catastrophic, and that is defined as tank rupture or fire, and it is generally associated with an extremely high cost event, or non-catastrophic. So the failure or fault is contained within the tank, and it is a routine cost event. And then you should consider the various potential costs associated with that failure. So this approach can be used as a template to calculate cost benefit, and we'll take a look at it. So this is an example of calculating the probability of failure. Firstly, the probability in a population can be, as I said, anything between 0.5 and 3%, and here we're using 1.5%. So the current failure rate with and without monitoring is set at 1.5%, or 0.015. Faults detected with traditional monitoring, and I mentioned already traditional monitoring, so that would be offline annual dissolved gas analysis, temperature monitoring, load current and voltage monitoring, pump fan operation, etc. So 20%, as an example, can be detected with traditional monitoring. Faults undetected currently in that situation would leave 80%. And again, with and without monitoring, these remain the same. We remember that monitoring does not prevent faults. It just gives you visibility of their developing. So the efficiency of proposed monitoring, and I mentioned that dissolved gas analysis is the cornerstone of a monitoring system, but this can include a range of different types of monitors. And we could say, for example, 70%. And you can see now that there starts to be a divergence in the probability value. So not detectable with any monitoring, for example, it will never be possible to detect a fault that is directly associated with a lightning strike. And there are other faults which current monitoring technology will not be able to detect, or at least give sufficient advance warning of. So probably something of the order of 30%, as suggested by IEEE, would not be detected. Catastrophic failures, of those 1.5%, of the population that would have a fault, probably only 10% of those would be catastrophic. So the remainder would be non-catastrophic failures. That would be 90%.
Donald, can you hear me?
Yes, I can hear you, Haley.
We have some questions that are coming in. For example, can you go a little bit more into depth on the ratios with and without monitoring? Some of them seem to be the same or close to being the same.
Yep. So the as I mentioned, the ratios for with and without monitoring are in actual fact the same until you start to get down to considering catastrophic and non-catastrophic failures where you see a divergence. So we can see, for example, that with a monitoring solution where we are suggesting that 70% of the faults can be detected with this advanced monitoring, that gives you, when you consider 10% catastrophic failures, that gives you a divergence between the probability of failure without monitoring and the probability of failure with monitoring. So you can see that you have a lower probability of a catastrophic failure occurring with monitoring, and you have a lower probability of a non-catastrophic failure occurring with monitoring. The differences, I mean, are quite small. We're looking at 0.0012 without monitoring, and 0.00036 probability with monitoring. So I guess this is where the key is, that when you have monitoring, you do start to see divergence of the probability of catastrophic and non-catastrophic failures occurring. And again, just for clarity, catastrophic failures are where tank rupture or bushing explosion or worse occurs. And I mean, worse can be that there would be damage to adjoining or nearby equipment. So you could potentially have a huge high dollar failure event.
Okay, thank you very much, Donald.
Okay. So we've established a mechanism by which the probability of early detection of failure can be assessed. What financial benefits can be achieved from avoiding those previously undetected failures? Well, in fact, there are many, and here are a few examples. So early detection of a developing fault will reduce the cost of repair, and that follows the logic that if you detect it when it's in its infancy, the cost of repairing a fault at that stage is likely to be less than if it advances to a more significant failure. For a GSU application, there should be a value applied to loss of production and potentially the additional cost of providing or purchasing power not generated if that's required. In some instances, energy regulators will fine power companies for customer outages, and that should be accounted for also if that applies. Under extra strain should fail, the probability of which is probably a little bit higher, that there is the possibility then of an outage and customer outages, because you would have two transformers failing. Transformers are expensive assets. If required and if appropriately monitored, those assets can be operated marginally above nameplate rating, and we all know that. And there is your 100% rating, and then there is the conditions under which you can operate at 110%, etc. But you can push that perhaps a little bit more, especially in a grid which is close to fully loaded. And there's a commercial value to being able to get that little bit more out of your assets. There is a calculation, which we won't go into here, but which is a component of this financial model that would look at the value of being able to do that, and then the potential cost by accelerating the aging of your equipment. So it's been already said, monitoring cannot prevent failures, but it can be used to extend equipment life by providing visibility of when maintenance is required. So you catch those developing faults early and you perform maintenance, or you observe something happening slowly in your transformer and you take some action to reduce the speed at which that's occurring. And this can result in a longer average lifespan for monitored equipment and a possible deferral of replacement. So it's unlikely that all of the above will apply, because some apply, for example, to GSUs. But considered individually, the impacts can still offer considerable savings, and we'll take a closer look at the final one, which is the ability to extend equipment life. So this is an easy to convey example, and it relates to the potential extension of equipment life if you monitor it over its entire lifetime, and then relate the benefit achieved to the cost of money. So we're all probably familiar with the Bathtub Curve, and this failure probability curve is associated with a huge range of technologies, but is often used to illustrate a transformer lifetime failure and is considered representative of a population of transformers. Here we see some infant failures, and that after the first few years, failure rate is generally low and steady until you get to 30+ years of age, and in some populations that will be 25, and some it might be 40. So this is the first curve, and it represents transformers without monitoring. At some point, the failure rate will rise to a point where it will drive automatic acid replacement. So there will be a point at which a utility will say that the probability of failure of this equipment is so high that we will simply automatically replace it. However, if you apply monitoring, and based on the assumption that it will capture faults earlier and that it will give you insight into your transformer that you otherwise wouldn't have, the likelihood is that you will be able to offset that bathtub curve. So the infant mortalities will be lower, the steady state failure rate will be lower, and the time at which you reach worn out and the speed at which those probability of failures increase will be less. And the difference between the point at which failures become replacements become automatic without monitoring and with monitoring will be X number of years or X number of months. So the benefit from deferred replacement is directly proportional to the current interest rate and the capital cost of a new unit. And this is the way I've presented it here. There are other mechanisms by which it can be calculated. But if we simply look at the cost of the money. So again, totally for illustration purposes, replacement value in a transformer, $4 million, interest rate on corporate loan, perhaps 4%, and IEEE actually detail it, I think, at 10%, but that's perhaps not current interest rate. So the benefit of every additional year transformer replacement is postponed is $120,000, and that's simply on the basis of the cost of that money. For each additional month year, the monitoring helps to defer the replacement of a transformer, considering savings in the value of money not spent can be realized. So here we have another example of cost savings looking at, and I should point out, example figures for a catastrophic failure. Earlier we calculated the improved probability of detecting a failure with monitoring, and here we'll see the dollar impact of that improved probability. So if you consider that the repair cost of a major failure is, and again example numbers, $1.5 million, the repair cost of a catastrophic failure is likely to be several orders of magnitude higher, and here we put $5 million. Early detection repair to a major repair ratio is about 20%. So if you can detect it earlier, the likelihood is that the cost of repairing it will be much less. So instead of $1.5 million for a major failure or $5 million for a catastrophic failure, you would spend $300,000 repairing that developing fault. As already said, you cannot prevent failure by monitoring. You can just take action on the basis of the monitoring. And then an online monitoring system cost, for example, $30,000, installation $5,000, a lifespan of 20 years, and a maintenance cost of $500. So these are figures just to illustrate. And then back to the probability, we already went through the process of calculating the probability of catastrophic failure with and without monitoring, or major failure with or without monitoring. And that can all be put into a calculation. So the probability of a major failure without monitoring and with monitoring. And I mean, if we look at the bottom line, so the bottom line of the annualized repair cost without monitoring, you're looking at, based on these probabilities, a total annualized repair cost without monitoring of $19,000 and with monitoring of roughly $12,000. So there is still cost associated. There's cost associated with the monitor. There's cost associated with performing those repairs that you've detected earlier. And in this case, so looking at this basic case of avoiding catastrophic or major failures by monitoring, there's a benefit of approximately $7,500 per annum. So there were two basic examples, but just to remind ourselves of the list of financial impacts that we mentioned earlier, so that we can just see the extent of the benefits that might be achieved. Early detection of developing faults to reduce the cost of repair, we've shown that. For GSU applications, there may be loss of production. We didn't go through a calculation for that, but it's a real cost. In some instances, energy regulators will impose fines, and they can be punishingly expensive fines. Again, does not always apply, and we didn't look at an example. Strain placed on other equipment, IEEE does give a guide for how that can be calculated, and we didn't look at it today. The ability to push the transformer a little bit harder has a commercial value. And while monitoring cannot prevent failure, it can be used to potentially extend the lifetime of the equipment, and there is a cost of money not spent, or a value of money not spent, that should be considered. So in conclusion, transformers can be better managed with monitoring, and this can result in an extended lifespan. The additional life can result in real savings in money not spent value. Transformers will fail catastrophically. There's almost no doubt about that. And the more utility have, the more transformers they have, the more likely individual failures will occur. But monitoring can prevent catastrophic failures by giving you insight into what's happening in the transformer, and the potential savings are relatively easy to calculate. Monitoring can also reduce the risk of unplanned outages and the associated lost revenue and potential fines that can occur, again by giving you insight into your equipment. And that's the final slide. If there are any questions or any discussion items, I'll open it up right now. Haley, thanks.